Hello, Royals. In lesson 6.3, we look at recursive sequences. The first sequence that we generated from that B family tree was the Fibonacci sequence, and it's not more important than any other recursive sequence, but it's a pretty good example here. In that, if you look at it, it usually takes a couple of seconds for someone to just figure out what's going on here. That you get 11 here because it's 8 plus 5. You get 8 here because it's 5 plus 3. You get 5 here because it's 3 plus 2. So what you're saying in a recursive sequence is that future terms depend on previous terms. It doesn't actually need to be plural. It could just be depend on the previous term, and it could be a large number of terms. The Fibonacci sequence of some future element depends on the previous 2. We'll see an example where a future element depends on the previous 3. The problem, though, is that that'll explain where the 11 comes from, where the 8 comes from, where the 5 comes from, where the 3 comes from. Explains that 2 is the sum of 1 plus 1. Sometimes people will say this 1 is 1 plus 0. But there isn't a 0 here. This is the first term. And those people can't explain where this 1 comes from. It's not a 0 plus a 1 back here. And then that 0 wouldn't have been a negative 1 plus 1. So you need some place to start. Often students start with the recursive case. They say that some future term, position n, is going to be the sum of term in position n minus 1, back 1 position, plus the term back 2 positions. Now these subtractions are in the subscripts. This is kind of like f of x minus 1, not 1 less than f of x. We're looking at subtracting 1 from the input, not subtracting 1 or 2 from the output. This should tell you, though, that you need 2 base cases. If you need to look back 2 elements, 2 terms, to figure out what some future term is, then you have to explain where the first 2 terms come from. This is often forgotten by students when they're asked for a recursive definition. They are your base cases. So why is the first term 1? Because I say so. Why is the second term 1? Because I say so. After that, the rest of the terms, you could say, develop themselves or follow a general rule. So we should include, sorry, no, that's that in the way, a restriction for this recursive case. You have your base cases and your recursive case, which works when n is greater than or equal to 3. Okay? One of the things that I pointed out, I think, at the end of the lesson is that arithmetic sequences are recursive as well. If I have a sequence a plus d, a plus 2d, all the way up to a plus n minus 1 times d, this right here is called the general term. And it's useful for being able to generalize. If you tell me, if you ask me to find, say, the 473rd multiple of 7, I don't think I want to count it out. I would want to use a formula that jumps right to there. But I can define this sequence recursively. Our first term is a, because we say so. And then any future term is going to be the previous term plus that common difference. And that definition works for n is greater than or equal to 2. Now might be a good time to show you that I tend to use recursive definitions talking about how to get term n. But sometimes the textbooks like to change things, and different formulas might want to change things. Let's try defining this in a different way. You say term 1 is a, and then to get some future term, the term 1 more than n, you would do term n plus d. And that will begin working when n is greater than or equal to 1. So your restriction on your recursive case kind of depends how you define your recursive case. This tells you how to figure out term n. This tells you how to figure out the term after term n. It might seem silly to use this approach after doing our general work in 6.1 and 6.2, but in a regular sequence, don't you normally know wouldn't you say we know the nth term right here and we're trying to find the next term? Kind of makes sense in that way. Okay, then the next thing I suppose I want to try talking you through is what students have the most trouble with in this lesson is actually looking at a sequence and finding a recursive definition. Let's give a recursive definition for. Now, we might be at a bit of a disadvantage here, especially if you've already read the lesson, because I mean, when you see it done, it kind of makes sense. What you need to practice here is a bit of grit. You need to try a couple of different things. You need to explain what is happening here in English if you can, and then try to translate it to the mathematics. I would suggest that you use other patterns that you're familiar with as well. So if you're thinking of a Fibonacci sequence, then maybe the first two terms are fixed here. Maybe I don't need to figure out how to get to 5 from 2. Because I don't want to say, oh, I multiply it by itself and then add 1, and I multiply by itself and then subtract 1. No, that pattern doesn't continue. I want to find a pattern that works in all different positions. I've seen people give me a different rule for how to jump from here to there, and that's not a predictable rule. Instead, you just kind of try different things. If I look at 10, I notice that 10 is an even number, so it's divisible by 2. I notice that all of these are also even numbers, and I start noticing that these numbers are divisible by 10. I start thinking of divisors and multiples, and I notice that 10 is 2 times 5. So I have a hypothesis. I wonder if a future term is the product of the previous two terms. I then check that hypothesis. 5 times 10 is 50. 10 times 50 is 500. If you can't write that mathematically, then write it out in English. But the expectation is for you to be able to write this out in English. Notice that the first number I tried explaining how we got was the 10. I don't have an explanation for how we get 2 and 5. So I'll just say the first term is 2 because the second term is 5 because any future term is the product of the previous two terms. Make it very, very clear that these are subscripts. That definition works when n is greater than or equal to 3. So you just have to try stuff. Sometimes students say, I can't do this, and I ask them to show me what they tried, and they show me nothing. That I don't know if that suggests that they tried nothing or if they were just staring at it and expecting it to become visible. You really need to do a bit of science on this, have a hypothesis, and then check that hypothesis. Let's jump to D, just because something different happened in example D. We've got 3, 5, 8, 12, 17. And you'll get more practice in your homework. So let's see, 3 plus 5 is 8. 5 plus 8 is not 12, though. That's 13. 8 plus 12 is 17. So you might start to notice a pattern here that if I do this plus 0, I get 8. If I do this plus this minus 1, I get 12. If I do this plus this minus 3, I get 17. But sometimes these patterns are maybe a little bit too complicated. See if you can find a simpler pattern here. Let's see, I tried adding, that wasn't working. Multiplying, 3 times 5 is 15. Divided by 2 is 7.5, plus 0.5 is 8. 5 times 8 is 40. Nah, that doesn't seem right. A piece of advice that I have for you is if you're having a hard time finding a pattern, try looking at the differences. So from 3 to 5, we're going up by 2. From 5 to 8, we're going up by 3. From 8 to 12, we're going up by 4. So if I can find a pattern in the differences, all I need to do is try to generalize the differences. Now, this is easy enough to write in English. The difference between the terms is going up by 1. That's a little bit harder to write in mathematics, though. So you might also find it useful to label that this is term 1, this is term 2, this is term 3, this is term 4, this is term 5. Because sometimes you can use that index. If you label that, your brain has more opportunities to make this connection. Notice that to get the second term, we add 2 to the first term. To get the third term, we add 3 to the second term. To get the fourth term, we add 4 to the previous term. So to get some future term here, I'm going to take the previous term and add the term number. This is kind of unique in discrete functions, because you're actually taking your input and your input is becoming an output value. And it's surprising as well that this isn't going to be a linear relationship, because it looks like, oh, I've got a slope of 1 on my independent variable, but there's also n minus 1 instances, or maybe n minus 2 instances of n built into this term. Okay. These sequences that we're looking at, unlike arithmetic and geometric sequences, let's say that they're purely recursive. I'm not sure if there is a way of generalizing them, of having a quick formula to figure out term 17. What makes them purely recursive is 17 was a bad example. If I asked you to find the 20th term of this sequence, you've got a lot of work to do, because you're going to need to know what the 19th term is. And then to figure out what the 19th term is, you're going to need to figure out what the 18th term is. And to figure out what the 18th term is, you're going to need to know what the 17th term is. If you get this, if you understand how this is going to be problematic, then you understand what recursion is. Okay. Let's finish this example up. This tells me how I get 5. It's the first term plus 2. It doesn't tell me how I get the first term. So tell your reader how you get the first term, and tell them when this definition kicks in. Okay. Recursion can be challenging. Generating a recursive sequence from a definition, I just skipped over because you're just sort of substituting in, but let me know if you're having trouble with that. I would anticipate that we have more trouble looking at a sequence and trying to find a definition that works. It will take more effort than you might be used to. Give it your best.